Because we are talking about isentropic law, we already talked about no heat transfer, right? We are already talking about zero heat transfer. We are talking about no work, right? No work done by the fluid and no work done on the fluid either. That's why your energy will be comprised of only two parts. One is thermal energy, which is temperature. One is the kinetic energy. So they add these two. They remain the same throughout the isentropic flow. Sounds good? Okay. Now, we can quickly have an example. You guys need to get your own shot. Don't be pretty crazy that sounds a lot. I did not know it would come so early. So hopefully you can get that solution. Now, let's look at the example. Now, gamma equal to 1.4, and let's say n is equal to 2.0. You will have T over T equal to 1 plus gamma minus 1 over 2 squared, which is 1 plus 0.2 times 4 is 1.8. So you know Tt is 1.8 times of T. In your textbook, you use T0. And the reason I use T rather than subscript 0 is that 0 can be so confusing. You thought it's a location, right? Because 1 can be a location, 2 can be a location, 0 is a location. Of course, 0 is the location where the velocity is 0. So the stagnation entropy is also called total entropy, meaning you add up all the energy or the relative energy. And the stagnation temperature is also called total temperature. That's why I use a subscript T. Okay. So you can do that part of interchange yourself. Now, so your PT over P will be equal to gamma minus 1. So it becomes so easy. You do it so many times, you do 3.5. Because when you are talking about air, gamma is equal to 1.4. All the diatomic gases we have, gamma is equal to 1.4. We have that. Monatomic gases that are 5/3. And once you get into CO2, H2O, it's more complicated because it has some structures where you need to look at the molecule whether it's living or not. So by the time you get to the triatomic species, there's no fixed phase at the bottom. But for monatomic gas and diatomic gases, you know, one is 5/3, the other one is 7/5. So it's 1.4. If it's 1.4, that exponent is multiplied. So it's calculated. By the time we get to this will give you 7.82. I'm not sure you need so many digits to understand the concept. Okay? You would do 2 or 3 digits, that's fine enough. But these are in your textbook. Okay, these are calculated. May I borrow one of your textbook? Can I borrow your textbook? Thank you. Page 628. This is for gamma equal to 1.4. So for example, the gamma 100 equal to 2 is here, right? So you have T over T0 is 0.5556. Well, that's nothing more than this, right? So you have T over TT equals to 0.5556. Take a simple one. So that's it. Personally, I like the other way. PT over TT over. Okay. So these tables are easy to make. Okay. What you need to do is just to plug in that equation. You can actually make your table, right? actually you are encouraged to do it because by the time you do the plan, move around, right? You just doing accounting for yourself. Now, of course, here you have T over T0 here. Rho over rho 0, you just use an ideal gas law, right? How do you do that? Ideal gas law is very simple, right? You would have rho T over rho is equal to what? P equal to rho RT, right? So, rho T is equal to PT over TT because R cancel out, right? Rho will be equal to P over so this will be PT over T times T over TT. So this will be equal to 1. PT over T, gamma over gamma minus 1, minus 1. Right? Because it's T over TT, we multiply the exponential, minus 1. So this is equal to T over T, gamma minus 1. And then if you want to relate rho T to rho with PT, you just substitute this in there. So, the rho T over rho, if you want to do this, right, what you would do? We do TT over T should be equal to, so you have TT, you have PT over P, which would be gamma minus 1 over gamma, right? And then to the power of 1 over gamma minus 1. So this is equal to PT over P to the power of gamma. It's quite a mess down here, but you can do it easier. The power is algebra. It's really, okay. It's really not a fancy or challenging already. Make sense?
Could you rewrite the bottom line?
Okay, last line will be rho T over rho equal to TT over T to the power 1 over minus 1 is equal to T over P to the power of gamma. And what's important here is not so much to memorize it, but just in case you forget, you know how to derive it. Right? So, part of your learning is you know why, not just you know what, right? So you can always derive this equation yourself. There's nothing wrong with algebra. Make sense? Questions? Now, the next thing we want to talk about, because of this stagnation properties, or related to it, would be we look at the mass flow rate, m dot. M dot is equal to what? Rho V A. Right? So rho V A, you can say this might be the conversion diversion number. But rho V A is the same everywhere throughout the nozzle, right? So you have this flow. Whether it's supersonic or subsonic, you don't even need to care about it now. Yes?
The PT over P, is it pseudo 1 over rho? For the tabulated that you just did?
Oh, yeah, 1 over rho.
Or next row again?
Is it right?
Yeah.
This is right. One over wrong. Or you can say, for example, how do you check? You can say PT over P is equal to rho T over rho to gamma, right? So you can see. Yes, right? Why don't you check the textbook for me? I think this is right.
That's right.
I think it's right. Because this will give you B over BT, meaning specific value. So this will give you P times B to the power gamma equal to constant, which is isentropic relationship, right? P times B to the power gamma equal to constant. That's also an isentropic relationship. So the isentropic relationship can take various forms, right? So 4 or 5 forms, but they are all related, so you can divide it. Okay, now, this other thing about the mass flow rate.
Volume to the power of gamma
Let's say
equal to a constant.
at any point your mass flow rate is really rho A. So you look at any location, you say the area is A, velocity, density is rho. That's what you have, right? So this will be equal to P over RT times VA. That's what I will do. But V is equal to what number? Times 1, square root of gamma RT times volume. Correct? Because the velocity at any point is equal to 1 number times the speed of sound. Now, so now you have P is equal to PT divided by 1 plus gamma minus 1 over 2 m squared to the power of gamma minus 1. T is equal to TT, 1 plus gamma minus 1 over 2 m squared. I just plug this in there, right? What you will find out is your m dot, and this part is algebra again, but do it once to convince yourself it's correct. Okay? This will be equal to PT times the square root of RTT times the square root of gamma times an area times 1 plus gamma minus 1 over 2 to the power of gamma plus 1 divided by 2, 1 minus gamma. M squared, M squared.
That's actually probably that.
So this is the mass flow rate. The reason that this is important is that you are referring to stagnation pressure and stagnation temperature, which remains individually constant throughout the flow, right? Rather than you talk about P and T, which varies with location. You might well just talk about PT. And in a case like what I draw here, because in the chamber or in the reservoir, T is equal to 0, T is equal to TT, P is equal to PT. Right? Now, how many of you have been to what we call building forms or where we have a supersonic channel? Have you seen? Go see it this afternoon. Yeah. You are an aero guy, you should see what the supersonic channel is, right? Otherwise, you say, oh, you got an aero degree. Have you seen that supersonic channel? Yeah. Some schools don't have it, so you're not allowed to, but you gotta go see it. out of your homework assignment. I don't collect homework and grade it, so it's okay. You can all see it. Which is for your own good, right? You go back to be with your family, cousins, and high school friends for your Thanksgiving and say, you're going to finish aerospace engineering degree in 6 months. Maybe they don't know how they should ask, right? They don't know what you're studying, but you can brag about it without invitation. You know, the aero guys, we talk about physical contact materials. Where area increases, the velocity increases. That's not what you see in a river, you know? They're really brag about it. Okay, now, here something is important because this all comes from isotropic flows. So that, again, the PT and TT will be constant throughout the whole flow field. And then PT and TT is what is in the reservoir. And the reason I mentioned supersonic wind tunnel that they're using the reservoir to drive this supersonic wind tunnel. So the thing about a supersonic wind tunnel is really something similar to this. So it's all the same. It's just that in a rocket, you just chop the other parts off and just let it go out, right? In a supersonic wind tunnel, you're trying to, you may have an open circuit, you may have a supersonic closed loop wind tunnel. But what happens is that you have this conversion diversion nozzle, and you get to supersonic flow, and then you have constant area test section. That's what it is. So in a sense, you can drive your supersonic wind tunnel using a rocket if you want. No more on campus, they will not allow you to do it. Let's purchase a new rocket. You can do it. I mean, they're all the same thing. Now, gamma will be somewhat different because your rocket may be burning some nasty stuff, especially the solid rockets. So, now, again, here's important that, so, at throat, M is equal to 1. So we call ATH equal to A star. This is the destination that you will use. A star is the reference area. Okay? So, what will happen is your M dot will still be equal to PT square root of RTT square root of gamma A star. And because M is equal to 1, so here it becomes gamma plus 1 over 2, gamma plus 1, 2, 1 minus gamma. But this is also equal to that, right? Because it's steady flow, whether you look at a flow or you look at it elsewhere, you have the same mass flow rate. You have the same mass flow rate. That means I can have A over A star. How do you do it? Just equate these two things and move things around, right? So this will be equal to gamma plus 1 over 2 divided by M 1 plus gamma minus 1 over 2 M squared. This whole thing to the power of gamma plus 1 divided by 2 1 minus gamma. So this is really a function of M and gamma. So that means for a given gas, as you know the gas, your Mach number is a function of area ratio. At any location to define the flow. Make sense? Of course, said earlier, if the pressure ratio is not high enough, you would not have A star because you would not have not equal to 1 condition in your throat, in your nozzle. But if you have it, then this is the case. Right? Now let's extend it a little bit more. Even if you don't have the A star, or even if you don't have Mach number equal to 1 anywhere in your nozzle, you still can imagine there is such a thing. You know what I'm saying? That's kind of like, from here you don't see the ocean, right? But you know what sea level is. Make sense? So that thing is a reference value, meaning that even if you don't have it in the context of your problem, you can imagine there is such a thing. Right? In a sense, none of us ever experienced 0 degree Kelvin, right? But now you better be convinced there is such a thing, right? Otherwise, all your scientific foundation is all gone. Because it's pretty serious, right? So here could be a gotcha question at your Thanksgiving dinner. You ask your cousin or someone, do you know 0 degree Kelvin? Does it exist? And he or she said, yeah, I don't know. I don't think so. You can say, then you cannot do any science with it. Just about. No science, no physics, no astrophysics, no astronomy, no chemistry, no biology, no nothing. Right? Even if you never experience it, it's there. Here, what we are saying is that then enjoy it in such a way that you will understand. So now, if you have another flaw, and let's say you never have a Mach number equal to 1 within your nozzle, but you can imagine here is your A star. Somewhere there is such a thing called A star. And you take the ratio between these two, then you would know your Mach number in the throat. The throat condition is not necessarily sonic condition, but if you have sufficient high pressure, then your throat condition is sonic condition. So your M throat is equal to 1, your A throat will be equal to A star. But in general, your A throat is just A throat, right? The A star will be somewhere in your imagination, right? So, the other interesting thing about this is your area ratio determines your Mach number from given gas. So, within the context of isentropic flows, it does not matter whether you have a big gun or a small gun. Right? You can have a huge rocket or you have a small rocket. As long as the area ratio is the same, you will produce the same number. Make sense to you? I don't know whether you were able to play with some model rockets, small rockets. I think after 9/11 disaster, this thing might be regulated more. When I first started teaching, students going, my rocket, there's a rocket store actually by Colonial in Alpha. They should go, can I buy a rocket? Yeah. Small rocket. And of course, it has the conversion diversion nozzle. And as you learn in your propulsion class, they will give you the specific impulse. The specific impulse is really the exhaust velocity divided by gravitational constant. That's really your specific impulse. It has the unit of seconds. So, if you want to jump your gun and you check out the propulsion proof, especially the rocket one, then you will look at the typical specific impulse of chemical rockets, right? Solid rockets probably give you 300 something, liquid rockets probably give you 200 something seconds. From the unit, specific impulse has the unit of time. And you know, when they show me this little carrot on the rocket, they buy it. Oh, specific impulse is the same. in the range of 200 or 300, but because the bottom rocket that you have tend to be the starting rocket. Specific impulse is 300 something seconds. That's like a real big fiber rocket, it's the same thing. Why? Because your area ratio is the same. If your area ratio is the same, your upper and the exit is the same. And if you are burning the same fuel, your temperature will be the same, so speed of sound will be the same, and n times square root of gamma r squared will be the same. That's the exhaust velocity. Divided by G is the same. Of course, when you have small rocket, the real effect comes in, right? Because the friction force on the surface becomes more important. Because in big rocket, you have this big exhaust, and your surface area is proportional to the radius, right? But your cross-sectional area, I mean, your circumference is proportional to r. It's 2 pi r. That's where you have the friction, right? But your exhaust is pi r squared. So when it becomes smaller, the frictional force becomes relatively important. However, in the idealization or as a first calculation, you can find out that it really does not matter how big your rocket is or the nozzle is. It is A over A star. That is important. Yeah. And that's also, so I'm following the textbook again. That is also in that appendix. The last one. So that means what? If I know what number, I will know this. I'll know this, I'll know this. So that's in the table. Okay. And you can make this table yourself. But this equation looks a little bit more important. And here you start appreciating that in high-speed aero, you have all these equations, and you will see it's always involved with gamma and n. Always. Even when we come to the shock wave, same thing. Shock wave is not isentropic, but we will deal with that separately. You can say that right across the shock wave, the process is not isentropic, but upstream of it and downstream of it will still be very close to being isentropic. Then you can handle the problem with 3 parts. Isentropic upstream, isentropic downstream, and shock across the shock wave, which is not isentropic. Questions for now? And this is really interesting. Again, you look at everything is gamma and n. So I always say gas dynamics sounds like music or looks like music. Because if you look at any musical score, it's nothing more like dot and stick. So 2 things. Yes, m and gamma in the music score. Dot and stick. One, you may have some tails. Those are like ornaments. Right? So gas dynamics, the high-speed aero is really like everything is gamma. You can say that you learn some scientific music here. Questions for me? Now the problem here is this is nonlinear, right? You have m squared here, and you have another m here, and you have power. So it is possible that for the same A, example, if A over A star is equal to 1.398, such an example is really how do I know it should be 450? But what I'm trying to say is that if you look up your table, this will give you 2 things. Not equal to 0.50 or not equal to 1.70. It has 2 solutions, right? If you think about it, you look at this location and this location, they're going to have the same area ratio, right? So if you think about it, that in a nozzle flow, that has not equal to 1 in the flow. The upstream and the downstream might have the locations where the area ratio is the same. But apparently one is a supply, one is a demand, right? So there are 2 solutions to it. So you need to exercise judgment whether it's supersonic or whether it's subsonic. Right? Then you can do it in several ways. If there's a nozzle attached to a reservoir, you know that on the inlet side it's going to be subsonic. The only location where the sonic condition will occur is at the flow. It cannot be anywhere else if it's attached to a nozzle. Right? But now, if you are talking about a supersonic inlet, you are flying supersonic, your inlet. So that part is considered a reservoir, right? The atmosphere is your reservoir. You are running the air. So it could be supersonic in the conversion side. Right? If that's a diffuser is just a reverse nozzle. Right? And we will talk about that. You really want to decelerate the flow because in a supersonic inlet, with decrease in area, the velocity, the Mach number will decrease. And you want to design it in such a way that the Mach number at the flow is 1, and then downstream of it becomes subsonic. Right? And then the subsonic air will go into your combustor. And because it's subsonic, there will be no shock wave. Right? If you allow the supersonic air to go directly into your combustor, there will be shock wave. And if there's a shock wave, it's not isentropic, the stagnation of the total pressure will decrease. Now, so let me digress a little bit. Stagnation pressures are very important concept because that's the total pressure you will have. Right? So in an isentropic flow, again, that stagnation pressure is the same throughout the flow. If you have shock wave, your stagnation pressure will lose. There will be a decrease in stagnation pressure. Stagnation pressure, in a sense, is the total ability that the gas, the total capacity the gas will have to work. And part of the work is expansion. Right? So when you go to a conversion diversion nozzle, your velocity increases to supersonic, your pressure decreases. And by pressure decrease, I'm talking about static pressure, because in a conversion diversion nozzle, it is an isentropic flow, the total pressure will not change, but the static pressure will change, right? And if the static pressure goes down, that means the gas is expanding, right? It expands, so pressure goes down. So these are two things, two sides of a coin. When you say expansion, that means pressure will have to go down, right? If the pressure goes down, that means expansion. And expansion does work on the gas, right? In what form? In pushing the gas to higher speed, right? So when you expand, you are pushing the gas to higher speed. And if you have higher speed, you have more momentum drop, then you have more propulsive force, right? Now, if the gas, or in this case, we are talking about supersonic inlet, if it comes into the combustor with a shock wave, that means the stagnation pressure will drop. So you lose the ability to expand because your pressure can only be less than your stagnation pressure, right? So let's say if your stagnation pressure is 500 kilopascal, you can expand to the atmosphere, which is about 100 kilopascal, 101.3. Now, if you have a stagnation pressure loss coming to the combustor, let's say it dropped to 300 kilopascal. When you expand it to 100, it's only a 3-to-1 expansion. It's not 5-to-1 expansion anymore. Make sense? So you don't want to lose stagnation pressure. This is an awfully important concept. Okay. When I was listening, it took me quite a while to appreciate it. But I hope you will appreciate it right after this lecture. Anytime when you talk about pressure loss, you are talking about stagnation pressure loss. It cannot be stagnant. It cannot be static pressure loss. Why? Because when the velocity decreases, static pressure goes up. So static pressure can go up or down. Stagnation pressure can only go down. If you are lucky, it will remain the same in an isentropic flow. If not, it can only go down. But static pressure changes, right? If you have a design flow just like this, kind of like going through sausage, before, etc., 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 etc. Your static pressure with alternative decrease, increase, decrease, increase. So when it increase, you can say, oh, stagnation pressure goes up. Stagnation pressure can only go up if you do work to it. What would be the case? When you pump the air into your tire. You think about it, the air in your tire is stagnation air, right? It's not moving, correct? So how do you increase it? You pump it, and that means work. Some pump is working on it. So you need to do some work on the gas to increase the stagnation pressure. Right? Make sense to you? The stagnation pressure by itself will not increase. It can only decrease. Pretty lousy situation, isn't it? It's kind of you cannot win, but that's kind of like thermodynamics technology. The entropy can also increase, right? So everything that we are doing is just trying to minimize it, right? Every day you clean up your room. You need to do some work to maintain that order. Right? Otherwise, your room is going, by natural direction, is going to be a mess, right? You can only become more chaotic. So stagnation pressure has that kind of quality. So you don't want to lose it. And pressure, you think about it, is able to expand. And in thermodynamics, this is the PdV work, right? PdV work is equal to, right? Now you think about it, pressure in fluid flow is kind of like voltage in electrical circuit because it drives the flow. So high pressure means a lot of ability to do work because you can expand. So I'm repeating myself, right? So you think about it, someone has a helium balloon and with a needle and polyurethane boom. Depending on your tolerance, it could be just annoying, right? Because what? The pressure is not very high, it's a piece of rubber material that goes in the air, right? Now, if you imagine you have a pressure reservoir on the size of a football stadium and 300 to 3,000 people, do you want to live right close to it? Right, or not? It's all contained. Just in case it pops, right? Yeah. And if it's just a small balloon, no harm, right? It's actually fun. When it pops, it's kind of unexpected from wow. Right? You think your friend is just being off, right? But if someone built a football stadium size 3,000 PSI reservoir there, you probably don't want to live within several miles, right? Just in case, right? So you all know that. Intuitively, you all know that. But you just translate that kind of thinking into stagnation pressure, and you know what stagnation pressure means. An intuitive understanding now. Okay? Now, so we know a shock wave. I can determine the Mach number in 3 ways now. I either look at the ratio of pressure or the ratio of temperature and stagnation to static, or I simply look at the area ratio. If I get one, I can check the Mach number, I can check the other two. Make sense? So these are all related. So you can say that your reference parameters for isentropic are these 3 things. These are the 3 most important things that you can think of. So let me quickly go through the next thing. For isotropic flow. Conversion nozzle. Let's imagine you have a reservoir. And then you have a conversion nozzle. Only conversion. So here V is equal to 0. You have P equal to PR. P equal to PR. R means reservoir. So this is stagnation also. Now, if I look at the pressure ratio as it goes, if P over PR, this is location X. Now let's say this value is 1. And here is your PP. Let's call it ambient pressure or back pressure. This word is being used in the textbook all the time. Back pressure is on the back side. Now, if I have the back pressure at the exit, which is the same as your reservoir pressure, that means there will be no flow, right? Because the pressure is the same. There's no driving force for the flow to happen. So, then you look at the pressure distribution, it will be more uniform, but there is no flow at all, right? Now, if I go down to my back pressure a little bit more,
I thought the ratio was PP.
then the flow will accelerate, right? It will accelerate, and it will accelerate. Let's say this is curve 1, 2, 3, and 4. And then at 4, when PP is equal to P4, Mach at the exit is equal to 1. And when you go to 5 or 6, the pressure will not change. Now, what I'm trying to say here is, if I reduce my back pressure from P1 to P2 and then P4, then the flow will accelerate more, right? As it should, right? Because the gas will see lower pressure in the backside. It will accelerate. But then it will accelerate only up to a point where the Mach number equal to 1 already at the exit. So that's condition 4. Right? That's condition 4. If you have a pressure of PP less than P4, Mach number at the exit is still equal to 1. And everything here, Mach is equal or less than 1. And everything here, Mach is greater than 1. Of course, the limiting condition will be 4, right? Condition 4. Now, the reason that you would have 5 or 6 being plotted like that is if I decrease the pressure PP to be P5, the flow will not change anymore. The reason is once you reach Mach equal to 1 at the flow, the gas cannot sense the signal downstream of it. Right? We talk about signaling mechanism. Because the back pressure kind of send out a signal. Yeah, I'm 20 psi, I'm 20 psi. And that signal can propagate all the way up to the reservoir. So the gas knows, yeah, okay, you are 20, oh, no, you are 50 now, let me accelerate more. But at some pressure, the Mach number at the exit is already 1. That means the signal which propagates at solid speed couldn't swing upstream. Make sense? You just imagine that the signal here it propagates the speed of sound. But then, here, the flow is already at speed of sound. So no more signal can pass over it. Make sense? It's kind of like if you are rolling upstream, and if the water speed is so high that you actually couldn't go further, right? So, or kind of like treadmill in a sense, right? Or perpetual swimming pool, because it provides you the speed, and you swim at the same speed, so that's still. So the signal, the acoustic signal of the back pressure, which is standing right there. So if the upstream gas couldn't feel any further change or any further lowering of the back pressure, this profile will change. It change from here to here to here. That's all possible because Mach number is less than 1. Okay? But once you go down to a certain level, it will not change anymore. Right? So by that time, if you look at this, M should be equal to 1. Right? You put in M equal to 1 here, what will happen? A over A star. Well, A is equal to A star, that's what it is. Right? So in this case, when PP is less than P4, A exit really is equal to A star, M exit is equal to 1. And your M dot will be equal to, if you put this in there, M dot over A star will be equal to square root of, PT square root of RTT. Plus 1 over 2, gamma plus 1 divided by 2, 1 minus gamma. That will be your mass flow rate per cross-sectional area. And we like this per cross-sectional area simply because whether it's big rocket or small rocket, this value should be the same. Right? That's a good thing to talk about. You want something that is very universal rather than special case. Right? So you will have this. So your mass flow rate will be equal to this. So it's proportional to PT means what? Even if when it's choked, in this case, the mass flow rate, this is the maximum mass flow rate. Or mass flux, you can call it that. This is already maximum. It cannot change anymore. Even you lower the back pressure to be vacuum, it doesn't matter. Because the fluid upstream of the flow will not sense the fact that it's vacuum out there. Okay? Yes?
If you only reach sonic speed, why in the graph does it say n greater than 0? What's the threshold?
Sorry. You're right. Okay. Everything's equal to 1. M exit equal to 1. That's what I'm saying. Yeah, right? M exit equal to 1. And this will be your maximum mass flow rate. So the nozzle is choked. Meaning it cannot let more mass flow rate to pass through. Yes.
So the extra energy is turned into heat.
No. Because you remember in this case, your PT over PE, let's say at the exit, will be equal to gamma plus 1 over 2 gamma over gamma minus 1. This is equal to 0.5283. Okay. Gamma is equal to 1.4. So that means your PE will be a fixed value, regardless what your downstream or the back pressure is. So what that means in the context of this conversion nozzle is that your gas will continue to expand outside the nozzle, right? So gas expansion outside the nozzle. In a sense, there's a waste, right? There's supposedly, you still can harness that expansion by adding a diversion section of it. And that's exactly what we will do in our next lecture. We will add a diversion section of it to harness it. So what you really want to have is a perfect expansion, meaning the exit pressure is the same as your back pressure. Right, if you could. But sometimes you cannot. You simply just cannot. For example, you have a launch vehicle that goes into the upper atmosphere in the lower Earth orbit. It's vacuum on it. You cannot expand into vacuum. Because then you need to have an infinite area ratio. So what will happen is you will have a rocket. You probably end up with a rocket like this. Conversion diversion nozzle. Snow White. Snow White's good. This just will not fly, right? The rocket is so small and conversion diversion nozzle means okay. It just will not work. So you will never get to that. So here, and especially for your launch vehicle, what you want to have is, even if you design it in such a way that your exit pressure is the same as the ambient, which is sea level, right? I mean, here, Captain level. As you go up, the back pressure decreases, all the way from one atmosphere to the other. And of course, we can try to take advantage of this by being able to adjust the area ratio. But eventually, you still cannot, right? Because it goes to vacuum. So the problem with a variable a nozzle with variable geometry is quite difficult because you need a lot of actuators, right? So for atmospheric flight aircraft, commercial aircraft, you have not much problem with that because you need to land, you need to, when you are ready, you need to have this flat. So you have a lot of actuators. But usually for space vehicle, actuator is a penalty, right? Because you need to put in motor, you need to put in mechanisms, and for every part of the hardware that you put in, so many more extra pounds of propellant you need to carry, so there is so many fewer pounds of the data you can carry. Right? What is your first thing?
Hello? Ow! I'm gonna ask him if he's in school. Will you do this yourself? Clarify perfectly.